purpose of this tutorial is to introduce the key daylighting simulation considerations and show you how to set up a daylighting simulation. During the tutorial, I'll briefly explain the model geometry and data considerations relevant to daylighting simulations, review the different report types and calculation options, and finally, review selected simulation results. Although full daylight modelling functionality was only introduced in Designbuilder version 3, it can be used on models created prior to that, as these already contain the input data required for daylighting simulations. It was previously possible to model the effects of reduced energy consumption in simulations and export data to generate zone illuminance maps using Energy Plus. But now that Designbuilder has integrated the Radiance daylighting simulation engine into the software, it's also possible to produce detailed daylighting results such as illuminance, uniformity, and daylight factors from the same model in either map or grid format. These results can also be used to provide standard reports within Designbuilder to gain credits under the LEED, BREEAM, and Green Star schemes. Designbuilder includes all the model data required for daylighting calculations. When you click on the Daylighting tab, this data is passed to Radiance, which uses a ray tracing calculation method to calculate the distribution of illuminance in the working plane. The model data passed to Radiance includes the visible reflectance of surfaces, site ground reflectance, window glazing transmittance, and detailed geometry including local and component block shading devices. Shading due to movable internal shading devices, such as blinds, is not included in Radiance daylighting calculations. The geometry used by the Radiance simulation engine is that shown here in the 3D visualization screen, rather than the simplified geometry shown here in the edit screen and the geometry provided to the Energy Plus simulation. So the effect of elements such as local shading, window frames, dividers, reveals and sills is included. You should first check that daylighting calculations are enabled in your model via the Activity tab. It's switched on here by default. Going to the Openings tab, you can specify all the required glazing data under the External Windows header. Here you can also input the window reveal, sill, dividers and frame details. I'll leave those details at their default values. The visible transmittance factor for the glazing is important for daylighting simulations. You can see the total light transmission factor at the bottom of the info panel after clicking on the glazing type. Here. If you have manufacturer's data for the glazing, you should input the solar, thermal and light factors. It's normally easiest to copy a similar glazing type, then edit the data as required. Here I'll copy this fairly typical uncoated air-filled double glazing and then edit the data. I'll call it daylight glazing. I can access the glazing material properties by clicking on the glazing material layers. Again, I'll copy the glazing type and create my own to enable me to modify the glass panes. I'll reduce the visible transmittance value slightly to 0.88 and select pane. Once I've modified and created the new glass pane, I simply load it into my new glazing type. Then load the glazing into the model. As you see here. You can see in the info panel that the new model data is loaded. The dataset used by Radiance for daylighting simulations also includes construction and site materials data that may not have been previously considered for thermal modelling. You need to use appropriate material surface reflectance values for internal surfaces, i.e. walls, floors and ceilings. Note that the reflectance is simply 1 minus absorptance, and is therefore a value between 0 and 1. This data can be found by navigating to the properties of the zone internal surfaces in the Construction tab, such as the inner layer of the external wall construction here. The materials already contain appropriate values for general use. However, if you need to use a different value, you must copy and edit the item or create your own material layer if the material is locked library data. The process for creating your own constructions is as shown for the glazing a little earlier, and is also described in the Construction tab tutorial. External surfaces also need to be considered. Whether these are parts of the model building with surfaces which reflect towards glazing, or external surfaces such as the ground and other buildings. The external surface reflectances of the model building are treated as described earlier for the internal surfaces. The ground reflectance value is accessed at site level. Under the Site Details header here in the Location tab. The surface solar and visible reflectance value used by Radiance is here under the Ground header. Further information can be found on all of this data by typing daylighting calculations into the search text of the help file. Reflection from standard component blocks used to provide external shading and to model adjacent buildings must also be considered. You simply navigate to the component block and specify whether the component block provides shade and reflection. Then enter the appropriate details. The surface reflection is a material property and can be accessed and edited directly using the edit icon here in the info panel. You can also edit the data for all component blocks here at building level on the Construction tab. Once you've input the required model data, you can open the Daylighting tab to input the calculation options. I'll call this Tutorial 1. There are 6 different daylighting report types that can be generated by Designbuilder. The first option produces a daylight distribution contour map showing graphically how illuminance varies in the zone or block displayed. The grid option provides summary daylight statistics, including daylight and uniformity factors, If you don't require a particular report type, you should normally select either the map or grid option. There are 4 different energy code report formats, which enable you to generate the data required to claim credits under the LEED, BREEAM and Green Star schemes. Changing the report type changes some of the defaults. See, for example, how changing to the LEED report type changes the working plane height here to 0.75 meters. Selecting the report option, which relates to your particular energy codes, such as BREEAM, will ensure that the correct options are set. Designbuilder provides 6 radiance option templates, which cover typical levels of detail, enabling you to select the appropriate level of accuracy for your particular analysis. The more detailed options improve accuracy but increase simulation time. Note that radiance uses a statistical Monte Carlo calculation method, and this introduces the likelihood of slight variations in results between iterations. The degree of variance reduces when the more detailed calculation options are used. Radiance calculations are also not necessarily uniform across the grid, as they put more calculation effort into sensitive areas such as glazed perimeters. This ensures that the results give the maximum accuracy for the level of detail selected. The working plane height here is the height above floor level in each zone at which the illuminance results are calculated and displayed. As I've just explained, this can vary depending on the particular energy code or certification scheme to be used, and is reflected in the report type. The margin is the distance around the zone boundaries where illuminance data is not calculated to minimise the risk of including potentially misleading information in the summary results. The default 0.5 metre margin is based on CIBSE recommendations. A number of different sky models can be used to provide different values for the external daylit illuminance. The CIE overcast sky is the standard traditionally used for daylight factor calculations, and is set as the default for most report types, though the CIE clear day sky will be used for LEED version 3 calculations, which are a special case. The maximum grid size is used for the general domain, and Designbuilder applies the minimum grid setting at perimeters where the layout does not fit the maximum grid size. The maximum grid size is the main grid size used to divide up the working plane when calculating illuminance. You should consider the size and number of zones in the building when selecting the grid size. A fine grid will increase resolution in daylighting outputs and increase simulation time, but a very coarse grid in a small zone may not give a good enough distribution. The minimum grid size is the smallest grid size that can be used to fill gaps in the working plane in cases where the maximum grid size is too large, especially at the edges of the plane. Use smaller values such as 0.01 meters to fill in most gaps between the main grid cells and the borders of the working plane for a more continuous output. It's common to use a minimum grid size that is a factor of between 1 and 0.2 times the maximum grid size. You should use a maximum grid size no greater than 5 foot or 1.5 meters for LEED EQ 8.1 calculations. Changing the detail level changes the advanced options. and more information on these is included in the help file if required. Click OK to start the calculation, which completes relatively quickly but does depend on the level of detail selected. The Daylight Illuminance Contour Map is the default display option and is the only display option available at zone level. At building and block levels, I can change the height of the map outputs. This takes a horizontal slice through the building, enabling you to view daylight plots in a number of blocks and zones at different working plane heights. So if I set that value to 3.7 meters, it shows the illuminance levels at a height of 0.7 meters above floor level on my first floor, as my ground floor block is 3 meters high. Only the two office zones are shown at this level, as the central corridor and reception are full height zones, and the working plane for these zones is at ground floor level. There are 4 scale options available. The building and block options show the calculated illuminance values for the whole building or block, with the highest and lowest values here used to set the range at the respective level. This provides a consistent scale for illuminance plots displayed at all levels when the building option is selected, and at block and zone levels when the block option is selected. I'll navigate to zone level and change the scale source to the zone option, which tailors the scale to the current zone, providing better visibility of illuminance and daylight factors at zone level. You can now clearly see the higher illuminance levels near the glazing at the office zone perimeters, with illuminance values ranging from 1396 lux down to 32 lux. You can clearly see the grid, with the 1 meter maximum grid squares in the majority of the zone and the 0.1 meter minimum grid squares used at the perimeters, where the 1 meter grid won't fit. The 0.5 meter perimeter margin is also clearly visible as the border between the daylight grid and the black line representing the zone boundary. The comparison with the first floor office is interesting, with the highest daylight levels on the first floor registering near the highly glazed internal wall, close to the large roof light where there's a clear view of the sky, but relatively low values near the east perimeter with the large external roof overhang shade, which reduces visibility of the sky from the working plane level. You can clearly see the difference between the unshaded northern and the shaded southern facades. The user-defined option allows you to enter the minimum and maximum values on the scale manually, enabling you to focus on the results in a desired range. For example, you may wish to highlight areas with daylight factors below 2%. So setting that as the high daylight factor limiting value will enable you to clearly see the distribution of daylight factors below 2%. Conversely, setting the low value to 2% enables you to focus on the areas with good daylight factors above 2%. If you wish to draw attention to areas of the working plane that have daylight factors below the entered low DF% value, then check this box to apply the scale to dark colour and define the colour in the colour selector below. I'll leave this set to the default dark grey colour. The apply scale to bright colour can be used in the same way to highlight areas with daylight factors above the high DF% value. I'll set the low to high daylight factor range from 2 to 10% and apply that using the tick icon. The large amounts of dark grey in this zone map clearly indicates that most of the zone has daylight factors less than the typical minimum required value of 2%. So daylight penetration isn't very good in this relatively deep planned zone. This could result in greater use of artificial lighting, which I'll discuss in a little more detail at the end of the tutorial. It's worth quickly looking at the fully glazed north-facing reception area. This has very high natural illuminance and daylight factors and would provide a naturally bright and fresh feeling internal environment with no need for artificial lighting during the daylight hours. You can also generate summary average daylight illuminance data at building and block levels. The grid display option is available at building and block levels and provides information on average daylight factors, daylight uniformity and illuminance values for each zone together with a total for the building. The grid option might be useful if you wish to export the summary data for each zone for further analysis in a spreadsheet. There are 4 different formatted reports available at building and block level. 2 lead reports and BREEAM and Green Star reports. Going to the lead version 2 report at building level, you can see that the working plane value here is highlighted red. This is because LEED uses 0.75 meters as its standard working plane height. Therefore, if LEED analysis is required, you would need to select that in the daylighting calculation options. I set my calculation options to produce the BREEAM report. So you can see that all the correct data inputs for BREEAM analysis were used in this top section of the report. The report shows that all of the large and relatively deep open plan offices fail on both the minimum daylight factor and uniformity criteria. The reports can be exported and saved in a variety of formats. The results provided in both the daylight maps and reports enable the designer to start to consider options to improve daylighting in the occupied zones, possibly ranging from simple measures like increasing the reflectance of internal surfaces to more fundamental changes like changing the glazing or external shading details. Making this sort of change may appear fine in isolation, but changes which allow more natural light penetration to improve daylighting can result in higher solar gains and hence higher zone temperatures or higher cooling loads in buildings with mechanical cooling systems. By including both thermal and daylighting simulation engines in one package, Designbuilder enables you to use one model to make a quantitative comparison of the impact that any improvements in daylighting would have on comfort conditions and cooling loads, so that you can optimize your design and minimize overall energy consumption. This tutorial has introduced the key model data terms and requirements for daylight modeling and showed you how to set up and run the calculations and review the results. Designbuilder enables you to undertake energy and daylighting simulations using the same model. This means you can take a more integrated design approach to ensure that the optimum design solution is achieved whilst minimizing modeling time and maximizing efficiency.